because it's always quite painful to have to go back and change those things later on if we find issues with it that are a detriment to the weld process. So, again, you can look at the overall part design, material selection, part size, shape. Those are all, factors that also play a role in this. But the joint design, becomes the real nitty-gritty detail. There's a specific set of features that is necessary to ensure that melt does occur and you get a weld in the intended location. So, just looking at, for example, this image on the right here, this is, a traditional, injection molded component that's being welded together. And, the weld joint is down right around where the top of the nest is, right? But you're making contact up on this surface with the sonotrode. We want to make sure that you don't melt this surface. We want to make sure that you drive the energy into the weld joint, which is down around the perimeter where the two halves come together. And as we go through this, you'll see that there are several different types of joint designs that would pertain to specific types of parts. So depending on what you're trying to achieve for an outcome, whether it's a hermetic seal or, you have a part that's going to be used in a way that it's going to see a lot of forces, maybe being handled roughly, drop testing, side torquing, and so it needs to be a really strong weld joint. So there's different types of joints that would be appropriate for different outcomes, and they all have their pros and cons where they shine and where maybe they might be a little troublesome. So as we go through those, you'll see them. When you look at the overall picture of a joint, and this is sort of the golden rules that we say that should apply to universally to any type of weld joint. These are critical factors that you should always try to include no matter what type of joint you're using. So I'll go through one by one and explain what they all mean. First one is the energy director. So the energy director in a weld joint, and keep in mind as I go through this presentation, I will get into more detail on some of these things. So I'm going to gloss over them for now, and then we'll drill down further as we go. So the energy director is a detail that concentrates the initial contact between what we call the driven part, which is this red component, and the fixtured side, which is the blue part. So imagine this being a housing, and this is like a cover that's getting welded in. So the energy director is the point of contact that's used to concentrate that initial energy and vibration, which helps to start initiating melt more rapidly. It also steers the melt to a very defined location. So you're telling it you want the melt to start here in the bottom of this channel, and the energy director ensures that that will occur. And again, I'll talk more about energy directors in the next few slides. Next would be sonotrode contact. So this is an overall point. You want to design your part ideally with a weld joint that is directly below the area where the sonotrode or horn would contact the top part. So your weld sonotrode makes contact here on this raised surface. Then you see that there is a direct line of sight straight down through the part into the weld joint. So you, for example, wouldn't want to contact the top lid over in this area because it's not above the weld joint. So you want to be in this region here because the direction of vibration and force is in this direction. It's in the Z axis. It's a hammering action that goes straight down into the part. Next would be support. So you have your vibration and compressive forces that are driving this cover down into the housing, but you also want to make sure that the bottom or fixtured side is properly supported, that it doesn't allow any deflection or compression. So the idea here is that the red part vibrates against the blue part, thus creating a frictional heat, which causes a melt to occur. But if this blue part is allowed to deflect, then that will dampen or minimize the vibration from between the two components, and that will then slow down or dampen the energy that's meant to go into the weld joint. So you want to have good support, preferably directly under the weld joint. Now, in this case, you've got this groove here where the joint is located, and it's kind of centered on this wall. And if you go straight down from there, as long as you had support at the very bottom, then this wall should be well supported. But if this were pushed out a little further into this cantilevered area, then you'd want to make sure that we had good support underneath this area to make sure that this region doesn't deflect. You don't want it to flex or bend outward under weld force. So the next one is melt encapsulation. So in this particular case, and again, I'll talk more about this type of weld joint later on, but this is an example of what we call a tongue and groove joint. And this particular design encapsulates the melt, because what's happening here is the melt occurs down in the bottom where this energy director is located. So you're going to turn this material into a soft, molten, flowing material, and as you compress these parts together, this material will start to flow, and some of it may ooze up these side channels here. But as long as you have something that's encapsulating it on either one or both sides, then that helps keep that glue, if you will, in place and around the weld joint. You don't want all that molten material to just flow away from the weld joint, because that is, in effect, the glue that you're using to hold the part together. So that's encapsulation. Next one is centering. So again, in the weld process, the mode of vibration is in the Z-axis. It's not a side-to-side movement, it's straight down. However, if your components that are being welded together are not somehow designed in a way that captures them, then there is a potential for like a side-to-side movement as you start to compress, that you could squeeze this thing and cause it to shift out of position. So you want to keep the outside edges aligned around the whole perimeter of the assembly. Then it's good to have some feature that keeps the red part centered to the blue part and prevents any significant side-to-side motion. So it keeps everything centered together and aligned to each other. And then the last two, 6 and 7, have to do with allowing travel during the collapse and also preventing landing on a hard stop. So what we're saying here is, when you look at this gap right along this outside edge here, before the weld takes place, that gap will be a little wider, because right now it's showing the energy director is already kind of pressed in or embedded in here. But imagine if this was at the point of contact here, a couple millimeters higher, you'd have a larger gap here. So during the weld, you're creating melt, and then you're squeezing these parts together. And when you squeeze them together, you want to allow so that you don't have a hard stop here preventing you from squeezing them together, because that's where you get your mix of material and your weld strength and your seal from. So you have to allow for some amount of travel here while you're melting this energy director. And at the end of the weld, you shouldn't bottom out these surfaces here. You should still leave a little bit of a gap. And I'll show you a little later on why that's important. Okay, so those are sort of the general guidelines that cover overall a good weld design, joint design. All right, so let's talk about energy directors a little more closely. Now, when we mean energy director, again, what we're saying is you're directing the energy from the vibration to a concentrated point.
Hey, Mike, can I stop for a second? We have a question.
Yes.
Okay, so how do you predict what part of the geometry will melt, and also what is the recommended witness line thickness after weld?
Okay, so the way that you would predict where it would melt, let me try to go back a slide. So when you look at the two surfaces that make contact first, so before the weld takes place, the only two components or the only two parts of this assembly that are making contact will be this little tip here, the energy director, and the bottom of this channel or groove. So that's the initial point of contact. There's no other contact going on. These are all gaps here. So when you start to vibrate, okay, the red part is vibrating against the blue part. The red part's moving, the blue part is fixed or stationary. And that vibration causes frictional heat as this surface hammers against this blue surface at the bottom of the groove. So that's how you steer or control where the melt takes place. It's at the initial point of contact between both parts. And in the different weld joints that I'll show a little later on, you'll see some different types of geometries that all demonstrate where the points of contact occur in different areas, and every time the melt will happen in those regions. And then there was a second part to that question?
Yeah, witness line thickness after weld.
Yeah, so the witness line thickness is more, I mean, it's more of a discretionary, I mean, there's no hard rule for that. It's just more what's pleasing to your eye, and it's scaled to the size of your part. You know, it could be a 1/2 millimeter on a really small part, or a 1/4 millimeter even, and you can get up to a couple millimeters on a really large part. Now, there are two components or two little details in a weld joint that would sort of dictate what that gap looks like. One is and it's not, one of them is not shown in this picture, but in this area here, you have basically line to line, okay, with a little gap there. Now, that gap is going to vary depending on how far you're collapsing your part during the weld. So we designed this feature, this energy director, with enough height to allow us to collapse a minimum, but then give us a little extra so we have some room to play with as we're developing the weld process to try to optimize it. Maybe we need to go a little further to get a little more strength or guarantee a better seal, for example. But at some point, you go too far, you over collapse, and then you start creating flash, or you might start damaging this surface from a longer weld time. So we try to find just the right amount of collapse that gives us that goal, or the seal, or the weld strength, without over welding. So we want to leave enough gap here, and there's a slide that comes up in a little bit that shows the relative difference, in an example, between like the height of this energy director and this gap before the weld starts. There are two dimensions, H1 and H2. So keep that in mind when we get to that slide, and I'll come back to that point. There's a secondary feature which again comes up on one of those details. It's a little, we call it a notch, or a cosmetic notch. That's just sort of a little superficial little reveal notch that notches in up here. And again, I'll show you what that looks like later on. So just hold that in mind momentarily. Okay, so back to the energy director. Again, what we're trying to do here is concentrate the stress in the material so that the weakest point starts to heat up and deflect first. Now, what happens here in a weld is you get two forms of heat generation or friction. One is going to be, and now granted this is not to a sharp point, you know, but just imagine if this came to a sharp point here, if this is carbon a sharp point. You're going to have a hammering action between the tip of that point and this flat surface. So that's one mode. But the secondary mode occurs with each impact. You're going to get what we call an elastic deformation of the internal structure of the material. So you're going to get an impact and then a compression and then a spring back. Impact, compression, spring back. And that's going to repeat 20 or 35,000 times per second. So what happens is during that compression, you get this sort of internal annealing of the molecular structure within the plastic material. So it heats from within. It's kind of like when you take a coat hanger and you bend it back and forth several times, and all of the molecules in the crystalline structure of the steel start to shift past each other, and that creates a frictional heat. And then eventually you bend it enough times and it will snap. But if you notice when you touch the material right there, you'll notice that it gets pretty warm to the touch. And that's that intermolecular friction of all of the molecules shifting around as you're compressing this material. So using very high-tech SpongeBob engineering, we will demonstrate an image of what that might look like. So you'll notice that the deflection starts to happen most dramatically at the weakest point, which is the tip of the energy director. Okay? So in a weld, you get that impact, and then you get a deflection, and that's how the part starts to melt in this region. Down here, what we're just showing is, without an energy director, you have a flat-to-flat kind of a situation going on when you first initiate melt, and now you have a much larger surface area that you're trying to heat up to start melting. And it takes a lot longer to get that to melt, and you end up putting a lot more energy and heat into this whole region where you don't need to. We want to try to keep the melt localized, like in this example with an energy director. We want to keep it localized to the weld joint. And that helps contribute to how and why we steer it to that specific area. So these next images, they're not images, they're videos actually, these kind of show more of a FEA analysis version of what we just saw on the previous slide. Instead of using a sponge, we are, oops, what happened there? There we go. Instead of using a sponge, we do an FEA analysis, and again, you see in both cases, and these are two different variants of a very typical weld joint, but again, you have your energy director here making contact, and then you see as you compress, you get this stress buildup within the material, causing heat, which starts these areas to melt. And during any good weld, what we're doing is we're not just melting the energy director, we're also melting this region down below. So as you get this material and this material molten at the same time and press them together, all of this material mixes and becomes a solid homogeneous mass after the material has cooled.
Mike, I have a question if you're ready.
Yep, shoot away.
Have you ever seen an application where the tip of the energy director acted like a knife and broke/cut the stationary part instead of welding?
I would probably say the most common area where we see that is when we're doing like filter embedding, when you are trying to weld a membrane to a injection molded part that has an energy director, and the membrane is thin, so it could be easily, there's kind of a fine line between getting it to weld in and cut through it. The other thing that I've seen is on some materials, and I'll talk about this a little more detail coming up, but on some softer materials, if you have an energy director that is too narrow and tall, it could mechanically fold over under trigger force before you've even started welding. But cutting in, I would say I've never really seen that before, but I suppose a scenario where that might happen is if you had an amplitude that was way too low, and you weren't getting good melt flow down into the lower part or the fixtured side. And so as you start welding, you're just kind of hammering the two components together, but you're not creating enough frictional heat to really generate or to get the melt started. So you might see more of like a pressing together, like a mechanical pressing rather than a melt and a weld. Hopefully that answers the question.
Yes,
Okay,
that answered it, Mike.
moving on?
Yep.
All right. Great. All right. So one more little illustration here, or demonstration to show the importance of energy directors. I'm going to play two video clips here, side by side, and one of these assemblies has an energy director, and one does not. Just to give you, just so you know what you're looking at here. These are actual welds in real time, right? Filmed with an infrared camera. So what you're seeing here is basically the side view of this assembly. Put this in perspective. This is about maybe between 3 and 4 inches tall, and maybe about an inch and a half in diameter. All right, so the weld joint is right here in the middle. All right, so one has an energy director, one does not. Play them both simultaneously. And let's see if anybody wants to take a stab at which one they think does and does not have the energy director and why. Hopefully you see, I'll play them again. You should see a pretty significant difference between the way those two welds look. All right, so if anybody would like to take a stab at that. I need to mute their phone. Well, that was an awesome sound. Okay, so would anyone like to take a guess? And can you all mute your speaker or mute your microphones, and then that'll prevent this echo from happening.
All right, so the reply, everything on the left has the energy director.
Yep, that is correct.
Yep, so everyone who answered that, Mike will send you something, right?
Get a high five. So what's happening here is, of course, the one on the left. All right, I think we still got some unmuted. Maybe that's yours, Jerry. I don't know.
No, I'm muted. It's when you have a phone and you're dialed in, that's what that occurs.
Okay, there might be a way to mute all.
I can mute all.
Okay.
However, that may mute you.
I don't know. Can you hear me?
Yeah.
All right, cool. All right.
Onward.
So the one on the left has the energy director, and it was obvious because the melt stayed localized in a very concentrated area, which is ideal. That's what you want. The one on the right had no energy director, so basically this design would be like a flat to flat. So it took a lot more energy and a lot more heat to get that larger flat to flat surface area to start melting. And so what you ended up with is this extra heat sort of migrated up into the walls of the part because it got, it was heating for so long, and it the extra mass, the volume of melt just caused that heat to radiate upward. And you don't need the heat up here. You're not welding here. We're trying to weld here. So that just helps to sort of drive home the point of the reason, no pun intended, the point of having an energy director. So a few details that we would normally recommend on the specific dimensions or shape and size of the energy director. And keep in mind, as I go through this stuff, you don't have to memorize these numbers. We're happy to send you, a digital copy of this, but, whenever you have a joint design or a part design that you're working on, you can always send it to us and we will review it with you and talk about the details and give you very specific recommendations that are tailored to your application. Because some of these numbers here are variable. They could change depending on a lot of factors on your part, like what is your overall wall thickness and what's the material and how big are the parts. And there are a lot of little variables that kind of go into determining what's a good energy director size and shape. So we just use these details here as sort of a rule of thumb, but just keep that in mind in the back of your mind that, if you have an application, let's talk about these details one-on-one and go through them. And we'll give you very pointed and specific advice. Again, no pun intended, haha. So just generally speaking, we try to shoot for an energy director angle of 90 degrees. That's a size that, or a width angle that works pretty universally for most applications and materials. In some cases, though, it's not possible to achieve that because we also have to try to shoot for a certain height. And this, again, goes back to that very first slide where I showed you like the golden rules, where you need to have some material here that has to be able to that's your sacrificial material that becomes the glue in your weld joint. So you got to have enough height here to allow for some collapse. So you turn this material into a glue. But if you try to achieve that minimum height, depending on the size of your part, and you see heights range from 0.3 to about 1 millimeter, depending on the size. And let's say you have thin walls, then if you do some simple geometry, you might realize that the wall isn't wide enough to accommodate the width at the base. So maybe we need to make the energy director, first thing we would ask is, could you make your walls thicker? But again, if, marketing department or the accounting department says, nope, we got to make them this thin to save 2 cents per part, or whatever the reasons are, it happens. I understand that. Then we look at maybe making the energy director a little more narrow. So you could go down to about 60 degrees safely, as long as the material isn't like a really soft semi-crystalline material, which is, like a polypropylene, for example, that's a little softer. You can like almost dig your fingernail into it and deform it. So those softer materials, when you start to go down to narrower 60-degree energy directors, they could deform mechanically before you've even started welding. So, 90 degrees, nice and robust, and usually sturdy enough to withstand that initial trigger force and not deform. We try to make the energy director as sharp as possible. Now, this specification, in many cases, may probably be somewhat unrealistic. 0.1 millimeter radius, depending on, again, on the material, the way that it molds and shrinks after a mold. How well the mold was designed, how good is the flow in the mold. That 0.1 millimeters is not always realistic or achievable, and that's okay. The point we're making here is to try to make it as sharp as possible. But if it's slightly dulled, chances are pretty good that it's not going to be an issue. And then lastly, we want to try to make sure that the height or flatness of the energy director all the way around the perimeter of your part is relatively flat. So you don't want waviness, high and low spots. The reason why is, especially if you are trying to weld an assembly that needs to have a watertight or hermetic seal. If that energy director has varying heights to it because of poor molding or maybe warping after the fact, then the high spots are going to make contact at the beginning of the weld, and you're going to start welding and collapsing, but you're going to have some areas where if the energy director wasn't as tall, it hasn't even made contact yet. So unless your weld collapses far enough to consume some of that lower part of the energy director, you may stop the weld at some point and then realize that there's leaks because you didn't consume enough of the thinner part of the energy director to create a seal in that area. So having flatness, good flatness all the way around the perimeter is very important, especially for a seal application.
Mike, I have a question.
Yes.
What's the lowest durometer material you could weld?
I am not an expert in durometer like ratings, so I couldn't really say, but I will say that just about any thermoplastic material is okay to weld. When we start talking about durometer, it becomes more significant when you're getting into what we call thermoplastic elastomers, where you have a thermoplastic and maybe you've put an additive in it that is a thermoset component as an impact modifier, for example, to allow the material to survive a drop test. Like some materials are really brittle. Those brittle materials are stiff and rigid and they weld really nicely. The more stiff and rigid the material is, the better it transmits that vibration through the parts to the weld joint. So a softer material, like some thin wall polyethylene and polypropylene stuff, might be a challenge to weld, but it depends again on how far away from the weld joint that the material is. I'm going to go back. I'm going to go back to the very first slide for a second to show you what I mean. So think about this here. You've got your sonotrope contact area, and then you have your weld joint somewhere down here. And the bigger the gap is from here to here, so let's say this weld joint was like down in this region, instead of being like 3 or 4 millimeters away, it's like 10, 15, 20 millimeters away from the sonotrope contact area. Now it becomes a little more critical when you're talking about softer materials, because now you have to transfer that vibration through this material down to this weld joint. And if it's softer, you get almost like a signal loss, if you will. You get some absorption and dampening of that energy. But if this material is really rigid and stiff, like polycarbonate, for example, or ABS, then you can get away with a little more of what we call a far field weld because it's still stiff enough that it will transfer that vibration with minimal loss. So, softer materials potentially can be welded as long as it's a thermoplastic, not a thermoset, first of all. And then secondly, we do film embedding, membranes, and those are, very soft and pliable, like paper almost, That's, of course, near field because it's a thin membrane, so you're hitting the membrane right on the surface and driving it in. But you have usually a hard, rigid backing or an energy director right behind it that acts as a stiffening agent that helps, acting as an anvil, if you will, against it. Does that help? Does that answer that question? Should we move on? Okay. Last thing we'll say about energy directors here. This would be like a top-down view looking at the top of the wall on an assembly. And one thing to keep in mind is if you have an assembly that is squared off, and you have a continuous energy director going all the way around the perimeter, and if it has to be a sealed type of application, you generally want to try to avoid a sharp 90-degree corner here. What tends to happen is as you melt this energy director and collapse it, you get in these corners, sometimes the material flows in odd ways and creates leak paths. And it's hard to predict how that's going to seal in the corners. So we recommend is if you have a squared off assembly and the energy director has to turn that corner, just instead of this sharp corner here, make it a nice sort of sweeping curve around the corner. And then this will result in a more even material flow in this area, and it doesn't act in unpredictable ways as much. Of course, if you don't need a seal at all for the application, then it's perfectly okay to just remove the energy director altogether in the corner. So you have energy director, and then it stops here, and then it picks up on the other side of the corner. Continues. And with that said, same thing applies for larger assemblies where you have long wall sections. If you don't need it to be sealed, it's perfectly okay to segment the energy director. So you have area where it's on and off, on, off. You still get usually a really good strong weld, and you're not going to get a watertight seal, but it's good enough to get a strong weld. And the reason we do this is to minimize the joint surface overall, or joint volume, melt volume, and it shortens the weld, requires less energy, resulting in less chance of damage to the part because of an extremely long exposure time. Okay, so we're going to now go through some of the basic weld joints and what they look like. Here along the top row, we have 4 fairly common weld joints that are used quite often. This last one here, not as much, but these first 3 are very common in most applications. So I'm going to just gloss over these, and then we'll go through one by one into a little more detail with some dimensions. First one is the energy director step joint. Okay, so this is basically a step joint in that it steps over. So you have sort of this is the red side is the driven part, and it steps over. You got an overlap here, all right, and then you have a basic energy director. The next one we call a tongue and groove joint. So you have the tongue side, this extended region here with the energy director, and then the blue part you have the groove that it fits in. That's a tongue and groove. Next we have what's called the mash joint. Now the mash joint's interesting. It is actually derived from one of these guys down here, which we call a shear joint. So there's 2 variants of a shear joint, and these down here are examples of not so great of a weld joint design. These have some issues that make these joints difficult to weld properly. So when you can weld them, and when you can pull this one off, it's a really good joint, but there are some issues that needed to be addressed. So we made a variant of this and call it the mash joint. And then lastly, this one here we call the double V joint. Okay, and then down here, these are the troubling weld joints that we want to try to avoid, or at least improve if you have something like this. One being the basic energy director, next the 45-degree shear joint, and then lastly the flat-to-flat shear joint. Again, I'll cover these in a little more detail here. First one, the energy director step joint. So this one is, out of all the weld joints, probably the most common one used in most basic applications. It's really good for overall just weld strength, mechanically holding parts together. Works well with side loading and shear forces. And it is self-aligning in that you have the overhang here. So, imagine this is symmetrical on the other side, so this cap cannot slide from side to side. And it's cosmetically clean in that it keeps, so this is the outside of your assembly. Imagine this region out here. And then this area would be the inside of the assembly. So imagine you have, something you're welding and, you're going to, again, this is the area that's going to melt. So you're going to consume this region. And as you collapse the parts together, you see this purple is the sort of melted material that flows out as you squeeze these together. And some of it will flow to the inside and could potentially flash to the inside of the part. In most cases, when we use this joint, that's irrelevant. It doesn't matter. Your concern is that just not to have the flash come to the outside. So you don't want it visible out here. Back to the question that came up earlier about the height of the energy director and the width of this gap. Okay, so this is what I was talking about, where you have this H1 dimension and H2. And if you'll notice here, we say specifically that H2, this gap at the beginning of the weld, should be larger than this gap at the beginning of the weld. So the height of the energy director dictates this gap. So that when you collapse these parts together, if you do need to consume this entire energy director, you still will have a little bit of a gap here at the end. And you're capturing and preventing this flash from oozing out. And then this is that secondary sort of reveal notch or decorative notch or edge, we call it. And this here, this is sort of a discretionary detail that you can add or not add if you want. The trick with this is it helps the human eye not see the variance in this tight gap. Because if you didn't have this notch here, and you bring these parts together and this surface comes line to line with this surface, and you look along the length of that seam after the weld is complete, most of those lines are not perfectly flat. They're not straight. So you'll see some areas that touched off and some that didn't. And the human eye can very easily detect the difference between no gap and some gap, even if it's just a couple thou variance. It'll look wavy. So if you put this notch here intentionally, right, this could be a millimeter, millimeter and a half, 2 millimeters, whatever. Again, this is something that you would decide relative to the scale of the size of your part that looks right. So this tricks the eye into seeing a wider gap. So as you go along the length of the seam, if that gap varies by a couple thousandths, you can't tell the difference as it varies slightly. Again, you can see the difference between no gap and some gap, but you can't see a 2 or 3 thousandths variance in a gap that's a millimeter wide. It's not easy to tell. So it's just an optical trick to make it look more professional after the weld is complete. Was there a question that came up, Jerry? Jerry, you there? I can't hear you.
Sorry about that. Can you hear me?
That's good. Yeah.
Is H1 always the max collapse distance, or can you collapse further?
If you had to collapse further, first of all, then you didn't design the energy director to be tall enough. You don't want to start welding into this thicker wall cross section if you can avoid it. Because what can happen is as you start, we call it over welding, you might start damaging, because once you hit this, now all of a sudden your wall gets really thick. You're going to slow down your melt, and you might start damaging this top surface here with the sonotrode. Additionally, I have a slide that comes up in a minute that shows this specifically, but you might start to see, because at some point then you will bottom out this H2 gap, and then you might see flash start oozing out here. So you could potentially create a secondary weld down here if these two surfaces come together. And this is not an intended area that you wanted to weld. You wanted the weld to happen here. And if that happens, that material that you start melting has nowhere to go. So it's going to shoot out this way, and it's going to manifest as visible flash. I have a slide that shows that. This one here is just a slight variation of the step joint that I just showed you. The only difference is that on this one, we have a nice symmetrical energy director, and this assumes that your wall is thick enough here to accommodate this. But if this is a thin wall and you can't get your energy director wide enough, then you can go with this, what we call a chisel joint. So you can get away with a thinner wall here, and yet you still get a nice energy director. This will kind of help steer some of that material also to the inside. So you get less flow to the inside of your assembly. More of it will probably stay down in this region, but you still have to have enough here to capture it. So at the end of the weld, it doesn't ooze out. But that's the only difference between the two.
Question, Mike?
Yeah.
Without a hard stop, how do you stop the top part from coming down too much or too little?
So when we weld, we control the distance of collapse in the welder. That's in your weld process. So there's a linear encoder, assuming that you're using a welder that can weld by distance. There's a linear encoder that you will program how much collapse you want. So knowing the height of your energy director here, let's say H1 was 0.5 millimeter, for example, tall. And when your welder starts the weld, it records this start position at initial contact before you've melted. And then it says melt 0.5 millimeter or something a little less than that. Let's call it 0.4, 0.3, 0.4 millimeters from this start point. So you start here and you collapse until you've traveled that distance, and then it will stop. You turn off, the welder turns off ultrasonics at that point. So that's how we control the amount of collapse. You don't ever want to program, or you don't want to design a part that welds to a hard stop if you can avoid that. So this example just shows the kind of assembly that's pretty typical that might utilize a joint like this, like a step joint. It's just a handle that has a weld all the way around the perimeter. Assemblies like this traditionally do not require a watertight seal because you have so many moving parts and buttons and triggers and things that there are already gaps and openings in these things. So, there's plenty of pathways for water to leak inside. So these are designed for one-time use. They don't get sterilized and used again, so they don't need to survive any kind of wash process or anything. So they don't need to be watertight. And again, you just have a weld around the perimeter. And in order to keep these two parts, the bottom half aligned to the top half, again, you have that step over feature that helps maintain that alignment between the two halves. This just shows, a real example of an injection molded part where we have a segmented energy director. So this is a rather large assembly. And you can, if you look closely, you can see like the energy director goes from here to here. So this is energy director. And then you have a gap here, and then there's a little alignment notch. The other part has a feature that fits in here to help maintain alignment as well. Then again, you have energy director here, and then once again here, and then down here. So this is segmented. It's not a full energy director. But the other thing I wanted to point out in this image as well, and this is more part of that overall general part design good practice, is anytime you have stiffening ribs or features inside the part, alignment posts or whatnot, and you have these sharp inside corners, we want to try to make sure that anywhere you have these inside corners here, that you don't have a sharp, it shouldn't be sharp like a 90 degree. You should put a radius, a little fillet radiuses in here, in these areas. Because during the vibration phase of the weld, that could cause some stresses and cause some of these features to crack. So you want to make sure that these are nice and robust and thick enough, and put a fillet radius anywhere where they meet the flat substrate surface. These images show a example of a before and after of a real welded part that's been cross-sectioned. So this is the chisel joint. So you see your energy director feature makes contact in this. You have this nice wide gap here. So we weld and collapse, all right, and then we section it, and you can see that there's no evidence anymore of a cross section. It's been totally melted, so this looks like it was molded as a solid mass. And you still have, now this one's a little bit exaggerated. You could probably stand to collapse this a little further if you needed to. But you'll notice, again, no flash came up and out. All the flash stayed to the inside of the part, which you don't care about this in here in this particular example. So this is what the consumer sees, and this is clean, optically clean from the outside. This would be kind of a starting point dimensionally if you were to design this type of weld joint. Again, keeping in mind that these numbers are not set in stone. They are recommended starting point numbers, and you would scale them to the size of your part if you can't achieve, for example, if you don't have a wall thickness that's 2.2 millimeters, that's not necessarily a showstopper. But if your dimensions, your general dimensions of your part are, significantly different from where we're starting from here, then we should discuss it and come up with a plan that makes sense, that fits to your parts, that will still give us a successful result. A couple things also to keep in mind. One of the things that we also recommend is like this dimension C here. We've got a little gap. Okay, so this does allow a little bit of side-to-side movement. You want free movement between the driven part and the fixtured part. You don't want your pre-assembly to be press-fit together where you have a lot of friction in this area. Because what that does is it dampens the vibration or the free movement between these two parts. So we recommend a small gap here of about 3 thousandths, give or take. So that's tight enough to not allow an extreme amount of slop, so you're still able to maintain a decent amount of alignment, but it still allows that free movement. Okay, next one, energy director tongue and groove. This one is a great weld joint if you're trying to achieve a watertight seal. The reason I like this one a lot more than the step joint for sealing applications is because you are capturing material on 3 sides, so you've got full melt encapsulation. Not that you couldn't achieve a seal with that first joint, but this one, that's not my first choice. This one is always going to be one of my first options for a watertight seal. This one is also lends itself to higher weld strength because you have a 3-sided sort of glue joint now instead of a 2-sided on the other one. One of the other big advantages of this one is it helps contain flash both on the inside and on the outside of the part. So I'll show you an example in a minute of why that's important, but anytime you are trying to stop flash to the inside, this is the best joint to use for that. Now, the drawback, of course, or the challenge with this particular weld joint is that it does require a pretty thick wall. So ideally, this wall is about just a little over 3 millimeters thick. Now, I know that's not achievable in many cases. That adds a lot of cost potentially to your assembly. And sometimes thicker walls create some mold challenges as well. So, if we come to a situation where we really want to seal and you're not able to achieve a wall that's thick enough, then we could discuss some options for maybe scaling this or maybe an alternate version of this weld joint. Now, this is an example of where tongue and groove really is practical. A lot of these type of assemblies that we do where you have a lot of internal fluid paths. Now, this is like, we do stuff that's used in surgical procedures where maybe there is like for example, heart surgery where they're pumping blood out of you and it has to go through a machine and then eventually goes back in. And it might go through some sort of a filtration system first, or if this is like a test kit for testing blood testing or whatever, and whatever passes through this cannot get contaminated with any particulate matter, then, having this tongue and groove joint, again, if this is the internal fluid path where the fluid is flowing through, then none of this weld particulate would be exposed in that area. So it keeps it cleaner to the inside. So, you've got fluid path and weld joints all through this whole thing. All in here. This is all welds happening. So this maintains a clean fluid path in applications like this. And again, here's a before and after of a tongue and groove. And this one also kind of nicely shows, I was talking about the sharp energy director. And this one here you can see, now granted this is probably slightly skewed or deformed because it was cut, mechanically before it was welded, but you can see this one is not perfectly round or perfectly sharp. If it's got a little bit of roundness to it, again, it's most likely not a showstopper, but just again, try to keep it as sharp as possible. But here you see the after, and unlike that first one I showed you, you don't see that flash bead here on the inside because all that molten flash is contained in here. So it's not exposed. So here's your fluid path in here that's clean. This shows high-speed video of a weld, and this is a magnified view of an energy director. So you can see what this flash would look like. You got all this particulate material that just kind of oozes out. So without any containment, some of this stuff can break off. You can see little chunks breaking away. So that's why that having that three-sided flash containment is important for applications like that. Keeps all that particulate captured. And then this one, this shows the same thing again. Now granted, some is going to come out this way because it's exposed, but you're not going to get anything that flows into these areas. Okay, so great weld joint for sealing applications where you need to keep a fluid path clean. And here are the starting point dimensions again, and you'll see if you stack all these E, F, and C, I think it comes out to about 3.2 millimeters, something like that. So again, we could scale this. I've pulled off this joint with smaller wall thicknesses, but we have to look at other factors. Is it a rigid material? Is it a soft material? And then we can decide the risk level of deviating from this design if we have to. Next one, mash joint. So the mash joint is one that works, again, great for sealing applications. The thing with the mash joint is it will give you the strongest of all of the weld joints. And the reason why this one, again, I'm going to kind of sketch something here if I can. Oops. Let's see. All right, so the original shear joint that I told you about has, I'm not a very good drawer, so please excuse me, has like a cutaway like this. It's like a 45-degree angle. So in that case, this sharp point here, which ends up acting as your energy director, would land somewhere on this surface with the shear joint. And the problem that you run into there is that this cover, you can't really control exactly where this lands. So it could land here, it could land here, it could land here. You have no control over that. So this cover might end up, this top line here, instead of being parallel, it could end up at an angle. So on the other side, if it was low on one side, it'd be high on the other. So it might press in crooked. It's not going to go in even. And that's the issue with that weld joint. The other thing that happens is because you have this surface here, as you start to weld it in, it has a tendency to want to deflect this outside wall outward. It's going to want to press those walls out. So what we've done is we've modified this. So we modify this, and instead of having that that surface that goes this way, we've ramped it upward this way. So now you have a sharp point here. It's an energy director, initial point of contact, but you have a hard landing spot so that when you first insert this cover at the beginning of the weld, it's going to land on this surface and align itself. You know, same thing on the other side. So you can't skew it crooked. And also, it does not want to press the walls out anymore because you don't have that sloped surface here. It acts like a ramp or a chisel, if you will. So that's the mash joint. The reason why this mash joint, oh, before I get there, this would be a good example of where a mash joint works really well. This is a water filter cartridge that goes in a refrigerator. And these covers get welded on. All right, so the weld joints right in here. And these weld joints have to be extremely strong and reliable. Imagine if you had one of these in your refrigerator and you went on vacation and this weld joint cracked or failed, and you would come home and your house would be flooded. So in order to have that peace of mind that it's a good strong weld, a mash joint in this case works really well. And they also seal really well also. And the reason why you get such a strong weld with these is because you've got this huge amount of intermix between both components at the end of the weld. You can see where it started, and we're gonna melt all this material, and we're gonna melt all this material here. And at the end, this cross-section of this weld is much larger than the cross-section of any of the other welds at the end. So this one's really strong. It's great for twisting, torque type loads, anything of that nature. Really strong weld joint. And here again, we have some basic dimensions to start with. Now this shows that the cover is on the inside. You know, if you wanted to have an overhang, that's fine too. And then lastly, the double V. So the double V is kind of it's a plan B, actually, as I like to call it. It's a fallback joint when you really want to use a tongue and groove joint, but you just can't get the wall thickness big enough to reasonably accommodate the tongue and groove. So the double V will achieve a very similar end result, but with a smaller wall. So you can go down to about 1 millimeter and still successfully do this weld joint. And as you see, instead of a 3-sided, you have more of a V-shaped. Now here you've got 2 energy directors effectively because you're making contact here and here simultaneously, and you're just gonna melt in. And this joint works fine as well. I would use the tongue and groove first if I could, but if I can't, then this one is a perfectly acceptable alternative to that. And here you see the difference between the unwelded and welded. And again, in all these, you know, you see that reveal gap at the end of the weld. But you look here, and this is one of the quality checks that we typically do with any welded assembly in our lab when we're developing a process. Is we'll you know, we could do a pull test or a leak test or anything like that, but we'll often cross-section the part after the weld, sand it smooth and look under magnification, and we're looking for no evidence of where the old weld joint used to be. Because if this was poorly welded, you might see like a knit line, or you may have mechanically pressed these parts together and got a little bit of a melt, but you didn't melt the whole thing and mash it all together and mix all this material, then you might see evidence of that. So when you see a smooth, homogeneous looking surface here, then that's a telltale sign that it's a really good, strong weld. Okay, so I mentioned earlier about what can happen. I think this is part of one of the questions that came up on what happens if you over weld and you collapse beyond the height of the energy director and you start getting into welding these flat to flat surfaces. So this is an example of what you might end up seeing. Is you're going to start welding here, and this is not where you intended to weld. So you close off this gap, and all of a sudden these two surfaces start welding. That material has nowhere to go. So as you start to melt it and squeeze it together, it's like if you put too much ketchup on your hamburger and you squeeze it, all the ketchup oozes out of the sides. The same thing happens here. If you over collapse, you're going to start showing flash. That's, you know, maybe you didn't intend to. If it's an assembly that gets embedded or buried in another subassembly and no one ever sees it, and you don't care about the cosmetics, then maybe you can get away with that, okay. But if it's anything that's going to be, the final product is going to be visible as welded, then, you know, this is cosmetically not too good. So that's why you want to allow for enough travel in the height of your tongue and groove depth and energy director height relative to this gap. So this, you know, your H1 versus H2 gap, so that you don't get to this point. You've already welded strong enough here that you don't need to overweld to compensate for that. And then one of the issues, you know, that you also need to be aware of is, you know, just in general, you know, part warping or mold accuracy are two common things that can occur. So this is an example of the mash joint, but you'll notice that the joint completely missed altogether. All right, so this little energy director here was meant to land here. But you see, we kind of pressed it together and it just, either this wall deflected out or this wall deflected in, or some combination of both. But that's usually a function of a couple things. One, potentially you had too much of a gap here. So this driven part was allowed to bias too far to one side, causing this to miss. Or the parts came off the mold and they were warped. So, you know, no matter how you centered this, you know, it would miss on one side or the other. Those are two common things that happen that you need to be aware of. So good molding, good quality molded parts is very important. We're almost to the end here, so I know we ran a couple minutes over, but we're pretty close here. Last couple things I'll say about these weld joints, the troubling weld joints. So this is, again, your basic energy director type design. This is fine. I mean, this is great that you have an energy director. You're going to weld, but two things happen here. One, you have no self-aligning feature between these two walls. All right, so if you bring these together, there's nothing that's going to prevent this red section from shifting from one side to the other. So you've got no overhang or anything. So in a case like this, you would have to rely on your fixture. So maybe you'd have to have your fixture come up and go up past the weld line and capture the outside here and then also on the other side to keep these two parts aligned to each other. And then the other issue is, of course, you have no melt encapsulation. So all of your weld glue is going to just ooze out and not help contribute to the strength of the weld because it's not staying contained in the weld joint. So again, this is that 45-degree shear joint that I told you about earlier that we've revised into the mash joint. And here again, you see where this point here lands in this spot, but when you first pre-assemble these parts, there's no guarantee that you're going to land in the exact same spot every time. It could land down here or up here and bias the angle or levelness of this cover. And here you have little to no internal melt encapsulation. If you go back and look at the example of our mash joint here, you know, we have this additional feature down in here that helps contain any flash to the inside as well. So all of your molten material, none of it oozes out and into the inside chamber. And then lastly, this is the flat to flat shear joint. And, you know, yeah, you have a hard landing spot, so you'll have no issues with this starting out level. But this is going back to one of the first slides where we talked about why you need an energy director. And here you see there is no energy director. So you have a larger cross-section mass of material that you're going to try to melt. And so you're going to get that issue with when I showed you the infrared camera weld, where you're going to get heat coming all the way up here and going further down to the walls. You might get some warping or stress and deflection here. And you also might cause damage on the top surface here when the sonotrode hits it. So simply adding that angled energy director right in here turns it into a mash joint, and all is good. And that's the end of it. That's